chapter 9 now. I know it's a rewind, but it's just the way things working. We did chapter 9 when we talked about sampling distributions of proportions. And then we moved on to confidence intervals for a single proportion, and then confidence intervals for the difference of two proportions. That was essentially what last week was about. So now we're going to do chapter 9 and return to sampling distributions, but this time of a single mean. And then we will move to estimate a confidence interval for a single mean. That's chapter 11. And next week, or maybe this week, I don't know how we'll go with time, we'll then move on and look at the sampling distribution for the difference in two means. So they're a kind of similarity, right? Proportions, single proportion, difference in two proportions. We're now going to do the whole thing from start to finish, but now we're going to do it with a mean and the difference between two means. So a little bit of this is overlap, but that's always good. So imagine that we have a population and we're interested not in some property that would be answered with a proportion, like what percentage are going to vote Republican or whatever, but we're interested in the mean of that population. So maybe we collect their age or their weight or something else. And you remember that funny little Greek letter there? It's called mu. Remember that guy? That's the population mean. And so we're going to be interested in finding an estimate for a population mean. And we're going to do that by collecting a small group of people, size n, and this is going to be our sample. Can anybody remember what symbol you use for the mean of a sample? What's the name of the symbol that we mean when we talk about the mean of a sample?
P hat.
Okay. Look like that, like that. Call it X hat. You say it out loud. So we're going to take the mean of a sample and use that to predict what we think the population mean is going to be. And there's another guy called sigma. And when you see sigma, doesn't that represent a population value, right? What does sigma tell you about the population?
Standard deviation.
Right. I'll just call it SD, right? Now, mu and sigma are parameters. Parameters are numbers you get from a population, right? And those are they're two of the most common. Isn't the other one, which we used last time, isn't P the population parameter, right? For the percentage of people who said yes to something. Now, when you get it from a sample, you have X bar, and you have another guy who's called S, or SD, or S with a little x, and isn't he the standard deviation of the sample? So those two, those are called statistics. So far, so good? Right. Now we're going to look at the theory behind sampling distribution. So imagine that you took a sample of 100 Americans and you found out what their age was. And their average age was 35, right? Oh, because this sample of 100 is 35, does that mean that the population mean is 35? My sample was 35, but does that mean the population mean has to be 35? No. Don't we hope it's close to 35, right? We'd expect it to be close, at least close most of the time, right? Now, what happens if you pick a second sample of a different 100 people? Do you expect the second sample to be 35? No. Every time you take a sample, isn't there going to be differences one sample to the next? Maybe this time it's 34.8 years. And then you do it a third time, 100 people, just make life easy. And this time it's 35.2. In fact, if you kept on taking lots and lots and lots of samples of 100, can you imagine collecting all of these? What you would get is called the sampling distribution, right? It's what you get from the distribution of all the samples you could possibly get. And it has a very particular shape. It has that shape. Can you imagine there was millions of these? Wouldn't it look like a big histogram with that shape? Right in the center, wouldn't the mean of the sampling distribution be the same number as the population mean mu? So for a sampling distribution of size n, it's going to be, number one, it's going to be normally distributed. What means it's going to look like that guy. And two, the mean of that distribution is going to be mu, the same number as the population mean. Because if you do it millions and millions of times, won't the weird ones kind of average out, and right in the middle, you'd expect most of your samples to be dead close to the real number, right? And the standard deviation, which we call standard error of X bar, but it's essentially just the standard deviation of this. It has a formula. Now, when we did population, wasn't the mean P and the standard deviation the square root of P 1 minus P over N? Remember those two guys? In this situation, it's got a different formula. It's that guy. Sigma, the population standard deviation, divided by the square root of the sample size, right? So if it's 100, it's the square root of 100. So can you imagine going 1, 2, 3, 1, 2, 3? Are we okay with the new formula? When you do means, it's this guy. When you do proportions, doesn't this guy become the square root of P1 minus P over N, right? Different formula, different situation. So far, so good? Right. Now, the rules for a sampling distribution to work.
Wait, so that sigma is just the standard deviation, right?
It's just the standard deviation of the population.
Okay.
And N is the sample size.
And we're finding SE of the mean?
You're finding SE of the sampling distribution, this shape here.
Okay.
Now, what are the rules for being able to do this? There are only two main rules that you need to use. The first rule is that the original population has to be approximately normal in shape. And we're very, very generous about what approximately normal is. It doesn't need to be a perfect, the population doesn't need to be that shape, right? It just needs to be roughly normal. To me, roughly normal basically means big in the middle and little in the ends, right? Doesn't mean have any great structure, but big in the middle and little at the ends is good enough, right? So don't be too pernickety about that. So what wouldn't work? Can you imagine your data had two distinct bumps? Right, if you knew that the population consisted of two bumps, don't do this. There's other techniques. Would you agree that badly skewed left and right would also be a bad idea? And what else? I guess, wouldn't just random nothingness also knock out, right? So as long as it's big in the middle and little on the outside, as long as it's got that rough single hill shape, you can get by with it. And number two is that the samples have to be big enough. And we have a problem with this. We never got together and decided how big is big. So I'm telling you my big. You need to have at least 30 people in your sample. That doesn't seem too, what's the word I'm looking for? Severe. Would you agree I'm not pushing it much? 30's, you know, a reasonable amount. Everybody should be able to get 30, right? So why is that a problem? This textbook and these WebAssign questions don't always follow that rule. So it's only going to be a question that they ask you specifically. You know, is this sample big enough? In which case, if it's bigger than or equal to 30, you're going to say yes. And if it's less than 30, you're going to be no. But there are going to be questions directly after that where they do a sample of 4 and they still do this with it. And aren't they breaking their own rules? That if you've got a sample of only 4 people, you shouldn't be doing this at all, right? But they're doing it anyway. So can you just live with that contradiction that WebAssign doesn't even follow its own rules sometimes? The only explanation I can give you is, do you know that WebAssign randomly puts numbers in things so you all get a different question? I suspect sometimes it randomly puts small numbers when it, you know, you'll do it, Eric, and it's 47, and I'll do it and it's 23, you know? It doesn't realize that it's breaking its own rules. So I don't know if that's a good description of it or not, but that's what you need. As long as these two are true, you can do this. So let's do a pretend question, then we'll look at some homeworks. Let's suppose I'm interested in the average IQ of OC students. So I collect a sample of 100 of you, and I happen to know that IQs are 100, and that they're, oops, let's do it from scratch, that the mean of an IQ is 100, and that sigma, the standard deviation, is 50. And I want to see, using that information, if I can estimate what the IQ of OC students are. So I get 100, and I found that their IQ was 110, because you're more intelligent than the average bear. And in this case here, right, I got a standard deviation of, let's say, 10. Now let's look at the sampling distribution question. Now, in the sampling distribution question, the mean would be the same, it'd be 100, and that the standard error would be sigma over the square root of n, which is 15 over the square root of 100, and so that's 1.5. So that would be the sampling distribution. So far, so good. That's the kind of question that they'd ask you. What's the mean and standard deviation of this sampling distribution? Okay, that would be a perfect world. That's using known values. Now let's pretend that we didn't know what the average IQ was, right? Because OC students are likely to be different than that, agreed? So what would their sampling distribution look like? So this is sample values. Well, it's sampling distribution changes. If you do not know the population mean, who do you think you use as your best guesstimate on? If you don't know that what mu is, right? Nobody knows it's 100. What would you use? Well, you use the sample mean. It's the only number you've got. So you'd use 100. It's an approximation. It's only perfect if they tell me that, but sometimes they don't know that, or we're not told it. We know a sample size, we know what we got, and we know the standard deviation of my sample. And what would the standard error of X bar be? Well, won't it be S over the square root of n, which is, in this case, is 10 over the square root of 100, which is 1. Are you okay with how to calculate the mean and standard error when you've only got a sample and nothing else? And how to do it when they tell you mu or sigma? If they tell you mu or sigma, this is the mean and this is the standard deviation. If they don't tell you this, but they tell you the sample information, you use this fella.
How would you discover the mean didn't have that backup?
How would
sample
it-
mean?
How would, which one, this one or this one? This one?
The bottom one, yeah.
Yeah, you would get it from the sample. Whatever the sample mean is, the sampling distribution mean will be the same.
So are we always going to have the sample and the sample mean?
You're going to have one of these two. Your question's either going to tell you this, or it's going to tell you that. but it
Okay,
won't
so we're
tell you both.
either going to have the sample mean or the regular mean.
Yes.
So what?
So they're only going to be one guy in town, so you'll know which one it is to use
So if we
because it's
have
the only one you've got.
the regular mean, we do the top one, and then if
Yep.
we have the sample mean, we do the bottom one.
Yes. We good?
Okay, I have a question.
Yes.
Because didn't you put that X hat was 100 down at the bottom, but X
Oh, it's
at the top is
110.
110.
You're right.
Okay, so then wouldn't that bottom part be a different number than 1 then?
Well, no, it's 1. This one is 1.5. This is different. This is 1.
Okay.
See, I'm using 10 over the square root of sample. 10 over square root of 100 is 1.
But won't it be over 110?
No, the sample is 100 people.
Oh, okay, sorry.
Right. There's a lot of hundreds here, but one of them is sample size. Right. Now, if I went and asked you to find a 95% interval, I'd call it a confidence interval. But I asked you to use a thing called the empirical rule. We would use it as an X bar plus or minus. How many standard deviations do you use when you're using what's called the empirical rule?
For 95, it'd be 2.
Right? And it'd be 2 standard errors, right? Standard deviation is standard errors. So in this case, X bar is 110 plus or minus 2 lots of 1. So that would be 110 plus or minus 2. And that would get me 108 to 112. So I've now answered the question I started off with. I would like to know the average IQ of OC students. Based on the fact that I have a mean of 110 and a standard deviation of 10, can I create the standard error from here? And then can I use the empirical rule along with X bar? And I can say that I'm 95% sure the average IQ of OC students is somewhere in the range of 108 to 112. So that seems reasonable based on our data. Okay. We'll do another one of them, but I'll only do the data one. I think when I mix and match, it's too much a distraction. So I would like to know the average age of the Scots people, right? So I collect a sample of 250 Scottish people, and I find the average age was 41. And I would like to create a 99.7% confidence interval using that data. Oh, and the standard deviation of my sample was 15, right? And I would like to create a 99% confidence interval using the empirical rule. Well, that would be the mean X bar plus or minus how many standard deviations for a 99.7, right? We're used to that guy. The standard error of X bar is the guy that's going to represent our standard deviation. And I guess I should calculate it. So here it is up here. It's S over the square root of n. It's 15 over the square root of 250. And on my calculator then, 15 divided by the square root of 250 ends up being 0.95. So we're going to be looking at 41 plus or minus 3 times 0.95. So that's 41, give or take, that's 5, carry 1, 2.85. So that's going to be, hard to do the subtraction, 1.85, I should be able to do that. 38.15 up to 43.85. So we are 99.7% sure that the average age of Scottish people is somewhere roughly, what, between 38 and 44 if we round it off a little bit. Now that was based on only a sample of 250 people. But that's a, you know, what's that? From start to finish, isn't that about 6 years? What would happen if I did the same situation and just by sheer luck, just to make everything else stay the same, that the mean was still 41 and the standard deviation was 15? That could happen, right? What would happen to my 99.7% confidence interval if I went through the whole process? Would it become narrower or broader? Do you agree? Come in the way? You can check this later, but I can tell you what the answer is going to be. That would be 3 times, that would be this line here. And so it would end up being 40.715 up to 41.285. Can you see how we have narrowed down the range of possible answers to within 1? Less than that, agreed? So doesn't it make sense that if you make big samples, you get better information, better data, narrower confidence intervals? Now, if I did this, it would cost an absolute fortune. Can you imagine how much money it would cost to find 25,000 people, interview them, you know, pay people to go and interview them, travel to Bristol and wherever it was? Well, it's not in Scotland, but, you know, Braemar, that's the one, that's in Scotland. Cost a fortune. Yet, isn't there a 0.3% chance I'm wrong? Right, as a 99.7% confidence interval, isn't it also a 0.3% chance that my interval is wrong? Can you spend a fortune and still not get an answer that's true? And there's no way fixing that, apart from spending an absolute fortune and doing it to everybody, right? You know, everybody in Scotland. Are we feeling a little bit comfortable about how to create these intervals now from samples? Because that's really the way you typically do it, isn't it? That's the way you tend to, you collect a sample and use it to predict, in some interval at least, where you believe the true answer to lie. Any questions about that before we start looking at some of the homework? You are allowed to ask questions. Oops, I just get signed out. I want to sign in.
On Cengage, it has this other assignment from chapter 9. Is that for today? Because the other two homework assignments are from chapter 11.
Yeah, 9 is from today.
Okay.
And then after this, we jump to 11. I know it jumps around a little bit. That's just the way it's working.
I was just curious.
Yeah. Okay, so this section that we're now going to look at is chapter 9, and it's the sampling distribution of a mean. And here we go. Hopefully, you should be looking at chapter 9. 10 questions. Right, let's get a head start on some of these questions. Maybe make this a little bit bigger if I can get away with it.
You have the key on.
Oh, I hate that. I keep forgetting it does that. Well, I mean, it's kind of useful when we have to check things, but it's annoying when we're doing it otherwise. It's too big. It's right. The first one is back to, remember the 2 rules that need to be true for you to be able to do any of the work, right? To be able to use the sampling distribution. So here's the first story. The mean normal body temperature will be determined by randomly selecting 18 individuals, and they get a mean of this number and they get a standard deviation population of that number, right? So are we allowed to do it? 18 individuals, is that big enough?
No.
No. Okay. Now, do you notice that later on they say that the population is approximately normal? So it isn't approximately normal number 1, and that's okay. So the guy we're looking for is number 2 being wrong and number 1. So population is bell-shaped in sample. However, the sample size is small. So wouldn't that be the answer that we would use? Sample size is 18 is small. Now, what about question C? The mean number of books owned will be determined from a randomly selected sample of 900 college students. 900 is big, would you agree? What shape do you think it might be? They don't tell us, but if you took different price textbooks or different samples, wouldn't you expect it probably as normal? You know, average price, some really expensive, some really cheap. So the blah, blah, blah. So however, so I believe that's everybody is happy, right? Both hold. Now, hopefully this one here has got both wrong. Let's find out. The mean number of books owned will be determined from a random selected sample of 4 students. Would you agree that's too small? And the data is skewed to the right. Would you agree that's number 1 is out as well? 1 is shape and 2 is size. So both of these are no good. So which one of them says both are bad? It's the middle one, isn't it? So that was basically giving you some examples where you're testing, is this particular sample allowed to be used in a sampling distribution context. Now, these ones are mostly getting you to calculate confidence intervals. So let's see what we've got. Oh, do you notice that they've given us population number, and a nice big sample? Would you agree everything's cool? Now, what would the mean be? It's the same as the population, so 7.2. What would the standard error be? Won't it be sigma 1.7 divided by the square root of 210 people. And so that answer would be 1.7 divided by the square root of, in this case, 210, and I get 0.117. Are you happy about the mean is the same as the population and that you use a formula for the standard, right? The standard error. Are we good? Oh, by the way, aren't they calling it standard deviation this time? And maybe next time they'll just call it SD. Who knows what they're going to call it? It's the same thing. Right. If you're doing a 68, isn't it going to be 7.2 take away 1 standard deviation? And then 7.2 add 1 standard deviation. And for a 95, it's going to be 7.2, take away 2 of those standard deviations. And on the other side, 7.2, add them. In a lot of ways, isn't this very similar to the stuff you did with proportions? Right. In proportions, your standard error would be the square root of p, 1 minus p over n, right? Here it's just s or sigma over square root of n. But that is pretty much it. Here's another example of it. If you did a sample size of 49 and then you did a sample size of 196, wouldn't you expect this one to be a smaller answer than that one? Right, bigger sample, smaller standard deviation. That one's pretty standard. I'll not do that one. Okay, here's some symbols for us. Here is some cholesterol levels and 28 heart attack patients. So I guess they looked at 28 heart attack patients and they got their average cholesterol level. And then they probably found, 100 or so healthy people and they got their cholesterol levels. And maybe they might find that there's a difference. And if there was a difference, maybe that cholesterol level is a risk factor in heart disease, right? That's how they come up with these things, right? They look at people who have, I don't know, kidney failure. And then they look at some other piece of information. Maybe it's lifestyle. Maybe how many alcohol drinks you take in a week. And they can get people who drink a lot get more liver disease than people who don't, right? That kind of comparison. So that's what this story is about, but they're only going to ask us for a symbol. So which one of these symbols here is going to give you the mean? And would you agree that it's a sample that's going on here? Okay, which one of these would give you the standard deviation, right? Well, if it was that one, and calculate the standard error, well, wouldn't you take, where is it? That number, and divide it by the square root of 28. Okay. Yeah, we've got time. Let's do this guy next. Vehicle speeds at a certain highway location are believed to be roughly normal, and the mean speed is 50. Now, I'm assuming that they've got a speed limit, and the speed limit is 50. And maybe that's why they're assuming that it's 50. Some people do 55, but they're probably not going to get a speeding ticket, right? Some people only do 40, and that's fine, whatever. And they take a look at that, and they've got a standard deviation sigma of 5. So these are population numbers, right? Population parameters. And they took a sample of 25. And now we're going to see what the sampling distribution would look like. Won't its mean be 50? and won't its standard deviation or standard error be sigma, which is 5, divided by the square root of how many people they asked them, which is 25. And the good news is, isn't that the number 1? Now, if you use the empirical rule for a 95% one, won't that be 50, take away 2 standard deviations? Which is easy to do because they're both 1. Where am I? I've lost the damn thing. Oh, here we go. So it's going to be 50, take away 2 standard deviations. So it might be as low as 48. And then it's going to be 50 plus 2 standard deviations. And it might be as high as 52. That's what we would expect a normal kind of sample of 25 vehicles to give you. Did you notice that 25 is too small? Shouldn't it be 30 or more? But will we just let that one slide? Because I mentioned that can happen at the beginning, right? We're still using the information. Now, we would expect somewhere 95% of the time that the sample would come out in some kind of range like that. So sample speeds for a random sample are measured at this location. Here's the numbers. Only our sample ended up being 58. That is not good news. Would you agree that 58 is way outside that range? Isn't 58 a lot higher than that range? So we have a problem here. This sample mean would not be consistent with this population value because it's well outside the possible range. So what we've actually done here is a little experiment. We made the assumption that the average speed was 50 miles an hour. We then conducted an experiment where we collected the speeds of 25 of them, and the answer that came out was much higher than the theory said it would be. Now, if we make the assumption that this sample is a fair representation of what's really going on, wouldn't the conclusion be that the average isn't 50 miles an hour on this street, that they're actually going significantly faster than that speed? Which, if that was true, wouldn't that be, I think we should put up one of those signs. You ever got them that tells you what speed you're going and tells you you're going too fast? They could do that. Couldn't they put speed cameras and get people to pay money and tell them that they're speed cameras? Maybe that would slow them down. Couldn't they just have cops with radar guns in very obvious places to get them to slow down? So if you know that a place is actually not obeying the speed limits very well, wouldn't this quick sample be a way of telling, right? You know, should we invest more money on getting the traffic to slow down here or not? Because can we pretend a different story, that this number was 51? Wouldn't that fall nicely within this range? So I would be saying, yeah, we don't need to spend a lot of money in that. Why do we want to put a cop there? He's probably not going to catch that many speeders. You know, don't you want to focus all your money and attention on places where they are breaking the speed limit, not in places where pretty much everybody's doing what they should be doing? But how do you decide? Well, this is one way to decide, isn't it? You know, I mean, you could collect that data pretty quickly. Couldn't you just tell a cop to go out on an overpass with a radar gun and tell them your job's not to arrest speeders right now. All your job is for the next 50 cars, put your little radar gun on them and write down what speed they're doing. Couldn't you come up with that information pretty quickly and tell whether a road is okay or not okay? At least that's what I would do. We've got a few more questions. Oh, any questions? Anything you want me to talk about? Does this seem reasonably straightforward how we're applying what we've got? Here's another one then. A fisherman takes tourists out fishing and he notices that over the long run, the weight of certain time is typically approximately normal. That's good. The mean is 12 and the standard even is 3, right? So we're assuming that's sigma, that's mu and that's sigma, okay? During a good day, the boatload of 8 people catch 2 fish. So this is a sample of 16 fish. We're going to create a normal distribution from that. So since it is approximately normal, the mean of the sampling distribution is 12, and the standard deviation is 3 divided by square root of 16. And that ends up being 3/4. So here's the story. Tell me the mean and standard error. That's essentially it, right? Here is a story. Tell me the mean and standard error. Right at the start, we talked about you can't use this sampling distribution unless 2 things are true. One is that the shape is approximately normal, and we're very generous about what approximately normal means. And the second is that the sample is big enough. Right? Look at this data. Do you think that this data is approximately normal? And be very generous about approximately normal. Just about make it. It's not freakishly weird. And that would be the correct answer. What about that one? Yeah, I think they're using words like, in this case, it's that one. It may be close to normal. You know, they're being kind of vague. And question 10, which I think is the last question. Let's check. It is. Okay. And even have a little used salt. So that's going to be a little bit different here. A recent article published in a medical journal stated that the mean amount spent per person on drug prescriptions was 450. So you've just told me, I'm writing this down because I need to find it, it's 450. And you've told me that the standard deviation is 54. And then I read it a little bit further and they take a random sample of 150, so that N is 150. And they found that the estimated mean spent per person on prescription drugs is 450. So in this sample, we have both things. Don't we have a mu and a sigma, an N, and don't we also have an X bar? So when they ask you to calculate the mean of the sampling distribution, you are going to use that number there, 450. Not the sample, but that guy. So what's it? How do we know? If they tell me both the population and the sample, pick the population, it's better. Now calculate the standard deviation. That's going to be 45 divided by the square root. How many people? 150. 45 divided by the square root, 150.
Why is that 45?
Yeah, I was just about to ask that. It's
It's not
54.
40, it's 54. And I did that deliberate mistake to see if you were paying attention. No, I didn't. It was a mistake. Okay, so 54 divided by square root of 150. And the answer I get is 4.4. What do you want? 4 decimal places? Okay. I have 4.4091. There we go. Now, do you notice that those two were using the population values, these two? Now, write a probability statement that can be used to calculate the probability of obtaining a sample of mean 440 or less. So which one of these four guys represents a mean of a sample, an X bar, 440 or less? Which one of these four dots represents that? A mean of 440 or less.
The first one?
Oh, wait a minute. I'm apologizing. 440 or more. Which one of those is 440 or more?
Is that the second one?
That's the second one. The question I asked a few seconds ago would have been the first one, but they want to know 440 or more. Right. Well, let's find that guy using salt. So what's the chances that you get a sample, X bar, greater than or equal to 440? Well, when I hit salt, I'm going to move this guy. I'm on a normal distribution. The mean of the sampling distribution was 450. Oh, I am not typing in 54. That's the standard deviation of the population, isn't it? What's the standard error going to be? Aren't we going to have to incorporate the N as 150? Right, let me come back and show you that. That's a population. That's a population. That's a sample size. And that's the sample mean. That's the information that we've got. The standard error of X bar, because we're interested in X bars here. It's sigma over the square root of n. So it's going to be 54 over the square root of 150. And that's the 4.409. There we go. Right, now I can return and use salt. So this guy here is 4.4091. And we want to be greater than or equal to 440. Okay, which one of these dots do you pick for a greater than? So you could be right, I didn't catch it.
Weighted.
There we go. And then we go over here and we make it bigger than 440. So the chances that you got the sample that you got happens a lot. Would you agree it's 98% of the time? So that's the number that represents the probability that you get a sample of that value or more. And that was the guy. And if I round it off to 4 decimal places, there we go. Are we good with that question and using salt? You want to see another one? Let's do another one. I'll make one up. Let's do quality control. You make cornflakes. That's what your company does, big production line. They're meant to be on average 16 ounces, right? Because it's a 1 pound bag of cornflakes you're making, right? And the standard deviation is 1.2 ounces. Okay. We from time to time, grab 100 boxes and weigh them. And in this 100, the answer that came out was 16.1 ounces. And we want to know what's the chances that you get a mean bigger than or equal to 16.1. The standard error is going to be sigma over the square of n. It's going to be 1.2 over the square of 100, which is 0.12. We're going to go to SALT to answer this question. The mean that we're going to use is the population mean of 16. The standard error is going to be the guy that we use for the standard deviation. And then we are going to use the one that does that. I'm going to do two versions of this. This is the first one. Here's, I'm assuming that, oops, I got the guy, here we go. I'm assuming that you're looking at SALT. Is that what you're saying, guys? Right, so it's a normal distribution. The population mean is 16 ounces. The standard error is 0.12. We want to know greater than, which is good. And we want to know what's the chances that it is greater than 16.1. And the answer that we get is about 20% of the time. Okay, does that seem okay? I mean, it's a little bit heavy, but would you be pretty comfortable that there's probably nothing wrong with the machine? And about 20% of the time, that's what you're going to get, right? So I wouldn't be too concerned that the machine that's putting them into the boxes is needing recalibrated, because you know that could cost time and money. Don't you have to stop the production line, take the machine offline, you know, do whatever you do to reset it, you know? All these things take time and money. So you don't want to do it unless you have to. Can we pretend that 2 weeks later, they do another, and this time it's 16.4 that comes out, right? It's worse than it was last month, right? Every box now is weighing 16.4. So we need to find what's the chances of that happening. Now, this time here, it happened about 0.20, or about 20% of the time. I don't think that would worry me. It's a little bit on the big side, but you know, that happens. Now we're going to do it a second time. Do you think this is going to be less likely? Do you think getting 16.4 ounces is going to be even rarer than 16.1? Well, the only thing I need to change is that one. Uh-oh. 0.0004. Okay, let's look at that. There may be a follow-up question. I like percentages. Would you agree that that's evidence that this machine's wonky? That it's putting too much cornflakes in the boxes, right? It's meant to put 16. The chances that on average, it's putting in 16.4, right? It's so small that it's probably a good idea that you go and fix the machine, right? It's, you know, whatever goes wrong with weighing machines, it's gone wrong. Because if you let this go, it's not bad for the consumer. Aren't you getting about 0.4 of an ounce more cornflakes every time you buy it? Right? But for the company, aren't they losing money by giving you cornflakes that they're not charging you for? And if you make 1 million boxes of cornflakes, wouldn't that add up to a fair amount of money at the end? So you don't want that to keep happening. So you would check it. Okay, a little pause here. Are we good so far? That we can now take samples and use them to predict probabilities of samples happening or find intervals based on samples. I'm going to move on to chapter 11. Are we good? Sort of a good. Okay. Give me a few moments to close this one off, and we'll be looking at our chapter 11 next, once I figure out where the heck it is. So we're going to be doing chapter 11, estimating the value of a single name. Almost done. Sassafras, hit the wrong button. Right, there's only 8 questions in this section. And let's jump right into the homework and show you what they're like. Suppose you're told that the IQ score for children in a particular school is 105.3. Explain what additional information you would need in order to whether to know that the mean was 105.3 is a statistic or a parameter. So I told you that the IQ of OC students are 105.3. How do I know that's a parameter, a population number, or it's just a sample number? What would I need to know?
Would it be that first option?
It would indeed. You'd need to know whether I asked everybody in the school, right, and I got their IQ, or whether I just took a sample of 100 kids. Because if it was everyone, wouldn't that be a population parameter, right? You asked everyone and you got the average IQ. If I only took 100 out of the school, wouldn't that be called a sample? A parameter is a population, right? A sample is a statistic, and that was it. Question 2. You've been told that for university classes, students are supposed to spend 2 hours studying outside of class for each hour inside. I wonder how many of you do that. You are curious to know the average amount of time that students really do study. So you contact what you think is a representative sample of 100 students at your school, and you ask them, how many hours of schoolwork do you do outside of class for each hour of class? The mean for the 100 respondents was 1.2 hours. Right, so we're just looking at this from a practical perspective. Right, so what is the population of interest? Which of those 4 represents the population in this story?
The students at your school.
Agreed. Right. Now, what is the research question you want to answer? So here are the 4 phrases for what we're interested in. Now, if we read this story, aren't we interested in how many hours they really do study, right? Per hour of class. So for students at my school, what is the mean number of hours of schoolwork done outside of class for each hour in class? Would that seem reasonable? What's wrong with the second dot? Because I agree with you, I like the first dot, but what's wrong with the second?
Says the median, not the
Yeah.
mean.
That's it. It's easy to miss it. And aren't we going to kick these 2 out because they talk about the state and we know the population's nothing to do with the state? Explain in words what the population parameter is in this study. Well, wouldn't the population parameter be a mu? Right, it's a population parameter. So for that reason, won't we totally ignore and not bother to read the first to the 4th dot? So, right, we're only going to focus on dot 2, this dot, or dot 3. This dot says the population parameter is mu equals the mean number of hours of schoolwork done outside of the class for each hour in class for all students at the school. Would you agree that is the correct answer? What is wrong with the one below it then? Say again?
The symbol.
Yes, it's a sample. Now, what is the value of the sample statistic? Now, if we go back to the beginning, isn't that the statistic, the sample they got, and the number was 1.2? So isn't this the sample? Why is that not? That's a population. This is a sample. Do you see the difference? X bar means it came from a sample. Mu came from a population. Are we good with this? All right. Now, in each part, use the information to calculate the standard error. Isn't this guy guess going to be 12 over the square root of 100, 63 square root of 49, 40 over the square root of 200? That is what it is. Let's move on to this one. The height, what we got? We got 27, we got 39, and we get 1. And we're being asked to do, the standard error, okay. So in this question here, isn't it just going to be 1 divided by the square root of 27, and that doesn't matter. And in this second question, the standard deviation of the difference is 5, so that's 5 divided by that square root. So standard error is standard deviation divided by the square root of the sample size. And there's different versions of what the sample might look like. With a bit of luck, I'll get this one done. Okay. Probably won't get it done because we are now moving to a bit of theory before I look at that question. Up to this point in time, we've been assuming that everything was okay and that you could use the normal distribution. But what happens when your data is really badly skewed or your sample is tiny? If either of these are true, then we can't do what we've been doing, right? We can't do the standard error stuff and normal distribution. And so you might think, well, that's it, you just can't do anything. But that's not true. There's another distribution, this is the first time you've met it, called the student T distribution. And it was created to deal with these situations, right? Where something is wrong. The data is just too small. The population is screwed weirdly, right? We can't assume that it's nice and normal. And we're very generous about normal, aren't we? Right? Big in the middle, little at the end. And even that was just not enough. right? It was just so badly skewed, you couldn't do it. Or the sample was just too tiny, you couldn't do it. So there's this new distribution called the student t distribution. And if you sketch a normal distribution, it looks like this. If you sketch a t distribution, it looks like this. It still looks like a hill. Would you agree? Would you also agree that it's flatter and longer? It comes down the way and it spreads out more that way. And the reason it does that is because when you've got small data sets or it's badly skewed, you have to have more spread in your answer. In other words, you're less sure about what the heck's going on. Very interesting side story. The guy isn't called Student. I can't remember what his name is, but I do remember something about him because I like drinking Guinness. He was actually a scientist who worked for Guinness. And in his part-time, he spent studying problems of quality control with very small samples. You know, you don't want to, you know, take a huge barrel of Guinness, right? And test it, because very often testing involves you destroying the product you're testing, right? It's very destructive testing. And he was testing things like alcohol content, viscosity, taste, and a whole wad of things, right? And that was going to cost them a fortune if they had to do 30 barrels every time they wanted to test something, even if they did multiple testing. He wanted to do it with as few numbers as he can. So he came up with this new distribution that works really well for very small samples or very skewed data. He wasn't allowed to publish with his own name because Guinness went and said, you know, this is proprietary information. We're using this to save money. We don't want the other brewers to know about it because then they'll save money as well. And we don't want our competition to know, essentially. But he liked it so much, he published it anyway. But he got around it by removing all references to anything to do with Guinness. He just made it pure numbers. And he used a pseudonym and he called himself Student. And that's how we know it to this day. So how does it work? Essentially, 90% of what you do is the exact same thing. You're going to go to SALT. You're going to use the same mean and standard deviation calculations that you always did. You're just going to use the SALT one. The SALT does have a few extra little issues, but let's just do a story right off the bat. Let's suppose that you're the Guinness guy and you've decided to test 11 barrels of Guinness and you were testing the average alcohol content. And the average alcohol content ended up being 5.4. And you want to know a range of values, right? For that particular Guinness production, right? What kind of range would we get, right? And let's show you how you do that. And I forgot to put in my standard deviation. I'm getting tired, sorry. You need all three, and I forgot to tell you the standard deviation. So the standard deviation ends up being 0.2, right? So what is the standard error? It's the same number that it's always been, right? And this guy is going to be 0.2 over the square root 11. And so 0.2 divided by the square root 11. So if we were going to do it by hand, the number we would do is 0.06. Let's just call it that. Now, if we were doing it empirically, wouldn't we just say 5.4 plus or minus, say, 3 of these and call it good? Well, let's see how SALT works. Click on this guy. Right. Here is SALT. Now, do you see a guy third from the top called T distribution? So you're going to click on that. Now, it starts off with a guy called degrees of freedom. And the degrees of freedom are one less than the sample. And there is your student T distribution. Doesn't it look just like a normal distribution? You agree? Same, well, it's basically the same shape. Now, what you haven't got here, and I'm going to have to is go here to inferential. One sample T, and we'll put in the sample mean, which was what, 5.4. The sample standard deviation, which was 0.2, and the sample size, which is 11. This one is a much better menu than the other one, right? Because we pretty much got everything that we want here. Now I want to generate a confidence interval. What kind of degrees of freedom would you like? 95? Not degrees, what confidence interval? 95? Right. Let's do 95. And there is that standard error. Remember that 0.0603? Hey, they do that for you for free. If we scroll along, can you see that the numbers for the lower and upper limit are the guys we want? So I'm going to call it 5.27, and the other guy is going to be 5.53. And do you know that little degrees of freedom where you take one away? Do you see they did that one for free as well? So I strongly suggest that you use the inferential statistics one, because doesn't it do most of the work for you? Are we good with that? Right, let's go and see what kind of conclusions we might come to. So he tested 11 barrels. The mean was 5.4% alcohol. The standard deviation was 0.2. This get done for us, and we have a 95% confidence interval. And that is the range. Okay. What would they do with that? Well, they'd probably have a kind of tolerance range. And what that would be is no two batches of Guinness are always going to come out the same, right? Aren't some going to have a little bit more alcohol, some a little bit less? So maybe their tolerance range is anywhere from 5.1 to 5.6. As long as it comes out in that range, they're happy, right? Based on this sample, would you agree that the machine is producing within the tolerance range, right? In which case your machine is good to go. If you got an answer like 5.9 to 6.3, suppose that came out. And this is your tolerance range. Wouldn't you say, wait a minute, this is much higher than what I'm willing to accept, right, in my typical variation of product. This is what I would expect. All these numbers are bad, right? They're outside the range. That would tell you that there's something going wrong with your system, right? If you were drinking Guinness, I don't think you would worry too much that it was had a little bit more alcohol in it, but I believe, you could tell me if I'm wrong here, don't you get taxed by the alcohol content of the drink rather than anything else? Is that the way they tax things in America? I believe it's how they tax it in Scotland, right? So whiskey has a higher tax than beer, right? So if you could buy a pint of whiskey and a pint of beer, a pint of whiskey will cost you more than a pint of beer. Not because it costs you more to make it, actually it doesn't. It just costs more because it's taxed more. So that would be bad news for them because they could end up having more tax to pay because of it. And I think that is a good place for us to finish. Now, some bad news and some good news for you. Is that the right way? You know, the good news first. Thursday is a holiday. The bad news, we're not teaching on a Thursday, so there is no holiday. So I will see you on Wednesday and Friday. Bye-bye. Oh, last name before you go.
Thank you.
You're welcome. I'll hang about for any questions if any of you have some.
I have a question.
Yes. What you got?
Can you show me how to use salt again?
To do what?
The homework that's due tonight.
Homework's due tonight. That's a hard one for me to tell. Let me have a quick look. I can't find it yet. I'm still looking.
It's okay.
I found it. Okay, so we are talking about sampling distributions of a single proportion. That should be, why is this back to front? Where's the double proportion one? I've lost it.
Hold on, I'm looking. So
Yeah, you tell me, because I seem to be missing one here. Or maybe it's just in the wrong place, because sometimes things get put in the wrong place.
mine is estimating the single proportion sample.
Is that the one you're on? Estimating the value of it?
Yeah, I mean, I haven't gotten yet to number 10, but I just know, like, I'm looking at these salt questions and I'm like, I'm lost and confused on.
Okay, let's
on them.
unlose you and unconfuse you then.
Okay,
So I'm on right now, estimating the value of a single proportion, chapter 10. Is that the one you're on?
yeah.
And I'm looking for, what's your last name so I can find it quicker?
Folks.
You haven't any answers done, is that correct?
Right, I haven't done that one at all, but like, I've been in.
That's fine. We can
Okay,
just checking it's the right one. Okay, so.
I
if
just
don't-
remember exactly where to like go and put in all this stuff.
Right, I'm scanning through this one, and this is the one that has only a couple of salts. They start at 13, so let's look at that one then. Right. Closing a lot of windows here, and let's see what we have. So you're looking at question 13 from that section.
Yeah.
Suppose that a new treatment for a certain disease is given to a sample of 200 patients. The
Mhm.
treatment was successful for 160. Okay, so I'm writing this down. It's 160 out of 200 patients. Okay, calculate the sample proportion. Right, now sample proportion, you could do without salt, but essentially it's 160 out of 200. And if you
Right.
divide them, you get 0.8.
Right.
Right, let's find out where the 95% confidence interval, because that's what you really want to know. Right,
Right.
you hit use salt. And then you make sure that you are now on a one sample proportion, which is that one.
Okay.
And number of successes meant 160 out of 200 people. So that's where those numbers go. So far, so good.
Yes.
Then you scroll down and you hit confidence interval.
Mhm.
And then you make that number whatever they want. I believe they want a 95. Let's double check. Yeah, they want a 95. So make that 95 and then generate results. And the numbers you want are, that's your lower limit and that's the upper limit. So let me copy this and paste it. This one first. So this one, oh, I don't need to answer there. That's where it rounds off to 3 decimal places, and that's what
Right.
the other one rounds off, right?
Okay.
So what we can say here is that based on this sample, we are 95% confident that this new treatment is going to be somewhere between 74.5% and 85.5% successful.
Right.
And we're 95% confidence that the true answer is in that range,
Okay,
which is what this sentence here is.
right.
And that's the end of that question.
Okay.
Right, so if we move on to the next one.
Those are about the same. That one's the same because it's a single, but isn't there one that there's like the double one?
Oh, there are double ones, yes. So we need to find a double story. Can you find a double one somewhere? Where's the double ones? If you can find one, I can do it because I know there is double ones.
Okay.
Oh, let's just pretend I know there's a double one, right?
Okay.
I'll show you how it works, right?
It's really just generating salt and utilizing that because I'm a
Okay, so let's suppose you had boys against girls, right? And boys were 14 out of 50, right? And girls were 15 out of 60, right? You had two different proportions that you wanted to compare. So
right.
you do two sample proportion.
Two
right.
sample proportion. Okay, yeah.
And the boys were, I'm making these numbers up, 25 out of 60 of them have broken a bone in the last 10 years,
Okay.
right? And in the girls, it was 15 out of 50 of them, right?
Yep.
Then you want to do a confidence interval for the difference. If you want a 95, leave that alone and you generate the result.
Okay.
And the lower limit is -6%. And the upper limit is 29%. So
Okay.
that would be from a -6% to a positive 29%.
hmm
That interval has 0 in it, right?
Right.
0 is in that interval. That means there's no evidence to say there's a difference between boys and girls breaking their bones, right?
Right, right.
If that interval was all pluses, then boys break their bones more often than
Okay.
girls do.
Right.
And if they're all negative, boys break their bones less than little girls do.
Right, right, right. Okay.
And